Hi everyone, I'm Pranoti, host of Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials or nanoscience, who tweets from the Real Scientists Nano Twitter account, which is realsci_nano. Hi everyone. Today we have with us Brian Pauw, who is a researcher at Pauw, Federal Institute for Materials Research and Testing. My name is Pranoti, and now we are going to take a deeper dive with Brian into his research and his life as a scientist. So, hi Brian, how are you?
Hello, doing fine, thank you.
Great. So, could we start with understanding your scientific career journey so far? Where did it all begin, Brian?
Well, I started out in the Netherlands. I studied until my master's degree at the Eindhoven University of Technology. These days, people call me a physicist, but I originally studied chemical engineering. Now, chemical engineering is a little bit special because I found that after finishing my studies, I didn't really know all that much about chemistry or engineering, but I know a little bit of both. I did during that time, I did a company internship at Teijin Aramid, and that's where I started to work with X-rays. And X-rays are absolutely cool. I mean, they're one of the coolest forms of electromagnetic radiation that you can work with. Now, after that company internship, I did a master's project, and back then I was really into computers, so I did it on computational chemistry. But after 7 months, I spent a whole summer sitting indoors behind my screen, and that was I found that was not quite what I wanted. So I kept in contact with Teijin Aramid, and they helped me set up a PhD project for which I went to Denmark. So I then went to the DTU, the Danish Technical University, in collaboration with the Riso National Labs and Copenhagen University and Teijin Aramid. So I had a lot of supervisors all over the place. I then did my PhD on X-ray scattering on fibers, because that was actually really awesome, because it was a complex problem that we were working on, and during that time I really wanted to get the perfect measurements, and I still don't have the perfect measurement. It's been 15 years since then, and I'm trying. We're getting closer to that, but I'm still not having the perfect measurement or the perfect analysis for that matter. Yeah, so after that, I went to do a postdoc for Aarhus University, which is also in Denmark. They sent me out to live at Spring 8 in Japan. Spring 8 is a synchrotron, so one of these places where they produce a lot of X-rays and have a lot of experiments around that electron ring. And I spent 1.5 years then at the synchrotron. This was in the mountains and pretty much in the middle of nowhere. And I could just see my blood pressure rise all the time. I mean, the synchrotrons are stressful environments. They have a very rapid move from one experiment into the next. All these experiments are 24-hour experiments. So to try and alleviate that, I applied for a second postdoc at the National Institute for Materials Science in Japan, NIMS. And there I could go back into the lab and actually refine more of the data correction methods that I was interested in. So I found that at the synchrotron, there was a lot of emphasis on getting a lot of data at very high speeds, but the data that we got wasn't really all that perfect. There was a lot of stuff, there was a lot of features and artifacts which were not part of our sample in there. So we were measuring a lot, but we had to correct for a lot of these things, and that was not implemented at that time. So yeah, I spent 3, 4, 5 years trying to perfect the data correction methods, the data analysis methods in Japan in one postdoc, which was quite long. And then after that, I got hired as a permanent researcher in Japan as well. We then moved to Berlin because our kid was born and went to kindergarten in Japan, and we decided, okay, well, maybe Japan is not the best environment for a kid to grow up in, for an international kid to grow up in that sense. So we wanted to put him in a more international environment, and what better place to do that than in Berlin, which is, as far as our experience goes, is one of the more international places that we have found. So yeah, I've been here for the last 6 years, pretty much continuing the same work. So they gave me an instrument at the institute, or they gave me a permission to buy a new instrument, and 3 years ago that was installed. So we've been working on that and improving that and taking it apart and making new software for it and so on. So we've done a lot of work on trying to improve this X-ray scattering method over here as well. So our working style is that we focus on the methods and the analysis, and that we invite material scientists to come to us and with their interest in materials, and then we try and take a look at it and see if this is a technique that can give perhaps some extra insight into this. So we do a lot of collaborations, both within our institute but also outside our institute. So yeah.
Okay, wow, that's quite a journey you had, from Netherlands to Denmark to Japan to now Berlin, Germany. That is really, really cool. How does it feel to be called a physicist when you started off your journey as a chemical engineer? Sorry, I'm not trying to be controversial here, but I've been a material scientist for quite some time, and there is quite a bit of back and forth, let's say, between chemists and physicists. I know you're a chemical engineer, but is that okay with you, Brian? Is it
of course. Yeah, no, I think in the end, it really doesn't matter. Whatever you study is giving you a starting point, right? And after that, you can go from the starting point in all kinds of direction. You can either go the more synthetic route, or the more computational route, or the more physical route. And wherever you decide to go, you will always find that you're lacking in information, right? You haven't got all of the knowledge necessary to do that. But that's also not what the university is supposed to do, right? That's not what the master's degree is. It's not supposed to give you all of the information and then you're done, right? No, it's you essentially never stop learning. You just continue and find ways to get the knowledge that you need to do the job that you want to do. So yeah,
absolutely. Yeah, sorry, I didn't want to be controversial there. As I mentioned, I was just wondering.
I don't think you're controversial.
Yeah, because as a material scientist, we are always tossed between, no, you're a physicist, oh no, you're a chemist, oh no, you're an engineer, actually.
So, why not all, right?
All of it, yeah. I say the same thing. We are all straight. But it sounds really cool. I mean, coming back to your career journey, it sounds very inspiring, and I'm glad you have the instruments now there. It's been installed since 3 years, and now you can do all kinds of cool experiments.
Yeah, I got very lucky, I must say. I mean, I have a lot of colleagues who also, in my eyes, should have deserved the same kind of luck and the same kind of success in getting permanent positions, for example, in being given the freedom to research what they want to research. Because if you're really enthusiastic about something, the research comes automatically, and you don't really need to put a lot of effort into it. Of course, there are moments that things don't work, or that you really have to process those hundreds of data sets, kind of balking against that prospect. But most of it comes relatively smoothly if you really like what you do, and that, of course, means that you need some freedom to do what it is that you really care about. Yeah.
Absolutely.
So yeah, lucky on the one hand. I'm also, your stereotypical white male, so that also gives me advantages that that others do not have. So I do speak from a position of privilege, and that is something also to keep in mind, that others may not have this privilege.
That is true. But I'm sure you've had your challenges as well.
Yeah.
But coming back to the research, your current research specifically at Pauw in Berlin, you already mentioned what are you doing, what is your current research. But what I want to understand from you, Brian, is where does your current research fit in this big picture of materials or nanoscience? Because materials and nanoscience is really broad fields. So where does your research fit in this big puzzle?
Yeah, so everything we measure is nano, right? I mean, because our technique, it doesn't really extend that far beyond the nano world. We can measure, as I said, with or as I might have alluded to already, with ultra small angle scattering, we can measure up to a few microns. But that's it, right? So we can measure everything underneath, and actually, the smaller the structure is, the easier it is for us to measure. So single nanometers, absolutely no problem. Our detection limits are really low there, so we can measure really small amounts of small particles. A few hundred nanometers, that's where things get a little bit complicated and hard to measure. But we've extended our measurement range also downwards, so we can now measure things like crystalline lattices and diffraction and wide-angle scattering and so on. We don't go quite as far as the total scattering people. I still think it's a bit of a misnomer, but total scattering goes to very, very wide angles, or actually very high scattering vectors. And we can't quite match that, because for that you need high photon energies in addition to measuring at wide angles, and on our lab instrument we just don't have the high photon energies to do this. However, we are collecting a lot of information from that angstrom size scale to nanometers and up to microns. So that is all nano. And the material scientists that come to us are they're interested in this nanostructure, right? Because as I mentioned, this really defines, or this can really define the physical properties of their materials, or the optical behavior of their material. So they're interested in getting nanoscale insight, and we do our best to try and see whether this technique can help them. It doesn't always work, right? There are, and I made a YouTube video about this, about sample selection for X-ray scattering. There are a lot of conditions that can sour things for us, right? That can make it impossible to do small angle scattering. Not enough contrast between your particles and whatever it is in is one of them, which is why biological systems are typically harder to measure. Things like proteins in solution, very low contrast for us. Or we can have things like fluorescence happening, right? If we have iron nanoparticles and we measure it with our standard copper X-ray photons, then we get a lot of fluorescence coming up, and then we need to deal with that. So some of these things we can deal with, other things we cannot. And in many cases, it's a matter of trying and seeing. Now, we are getting better at predicting whether samples make sense, and with our wide range of experience now with all kinds of different materials, we can reasonably accurate prediction about whether we will see something useful or not. We still sometimes fall back and say, okay, well, we'll just do a proof of principle measurement and see whether it makes sense at all to do these kinds of experiments. Yeah.
All right. That is really, really interesting, and I'm definitely really curious to learn about your science when you're taking over the account. It is almost like it is kind of a new world for me, because as I mentioned, X-ray scattering, it is a new world for me. I mean, I did some XRD back in my master time, I think. But yeah, that was ages ago, and I would love to learn more about it from you.
Yeah, and this is also where the history gets interesting, right? Because it has existed for more than 100 years, X-ray scattering. And I can bring up some of the earliest examples in my week curating this account, but I find that it's only over the last 15, 20 years that we've been able to really dramatically improve on the technique and on the reliability of the technique. And that was in no small part due to amazing developments in detector technology. availability of more and more computational power that we can actually correct for pretty much all of the practicalities in our in our experiment, right? The thing for all of the imperfections in our experiment, we can now correct for, or take it into account in modeling. And in terms of data analysis, we've also gotten much better since 15 years ago. There were a lot of people already in the 1990s who started developing this, and earlier as well. And I think that has really culminated into X-ray scattering becoming a very useful technique now. Mm-hmm. However, people don't know about this, right? Mm-hmm. Because they might look at X-ray scattering and go like, oh yeah, no, I tried that 20 years ago and it didn't really match and it was rubbish. So,
Right. Right. Yeah.
So, I'm trying to slowly demonstrate that no, it actually does make sense, or it makes sense now. It maybe it didn't make sense in the past, but it certainly makes sense to try it now.
Definitely. So, Brian, it sounds to me that you are, and you were also in the past, involved in a lot of really interesting research projects. And now my next question is, it's a toughie. If you have to pick one research project that you're most proud of, or the most fun or quirky one, could you pick one? As I said, I know this is a difficult one, but could you pick one and explain it to us in super simple words, please, in the section we call In Other Words?
I will do my best. There's one part which has actually resonated quite well with the scientific community, and that may be partly due to the title of the paper, because it was called Everything SAXS. Mm-hmm. And this was a review paper, right? But this was a review paper that combined a lot of very small investigations that I did for my weblog. Looking at nothing.com. Mm-hmm. And there I looked at what data corrections you could do, right? All of the data corrections you could do. Now it used to be that when you looked at data corrections, you would have to pick and adapt your data corrections based on the system you were investigating. And I found this very unsatisfying, because it means that if I'm looking at a biological system, I need one set of data corrections. And if I look at a materials investigation, maybe on metal alloys or something, I would need another set of corrections. And that doesn't make sense, because it's, in essence, it's the same experiment. Mm-hmm. So I thought, okay, let me take a step back and let me try and see what possible things I could do to correct my data, right? Mm-hmm. And so I combined all the data corrections that I could think of, and that was about, I think, 21 at the time or something. I think we've come up with 2 or 3 more since then. And I put them in the paper, and I said, look, these are all the possible corrections you could do. And we followed up on that later on, and we said, okay, all those possible corrections that you can do, well, you need to do them in the right sequence, right? Yeah. So yeah, exactly. So with the help of our colleagues from the Diamond Light Source, we actually implemented that in software, and we published a paper saying, okay, those data corrections, you can actually make a single universal data correction method that works for all the samples, at least all the samples that both we and them have thrown at it, mm-hmm. And gives you really good data without any effort, because you can do this in an automated fashion. So yeah, we followed up on that, and we made the flow chart saying, okay, these are the correction steps you want to do, and these are the measurements that you want to do for that. Mm-hmm. And I think that has given us a really powerful tool, because now we're one step further. Now we don't need to worry about, did I do my data corrections correct when you do the analysis? Because before that, you were doing the analysis and things didn't quite fit. You were like, is it the analysis, or is my data not correct? Let me go one step back and try to subtract a little bit more background or whatever. Mm-hmm. And you give the users all these sort of little knobs that they can turn and twist and adjust to get the data which they think is right, but may not be the right data. So we've wiped that all off the table, and we can now say, no, look, this is the data, and this is as correct as it gets. These are the uncertainties. Mm-hmm. And now you go to the analysis, and if your analysis doesn't work, that means your analysis is not correct, but the data is correct, right? That's reliable. I should hand out these certificates. I was in a Chinese shop this weekend, and I saw that they had this, I don't know what it was, a box of these medical supplements that you can take, or health supplements, and that one came with a certificate with a picture of somebody saying, "We certify that we strive to do our best," or something like that. I was like, I should do that with my data. Right? Here's the certificate.
That's a very good idea.
Saying that we really did our best. Yeah. Anyway.
Right. Wow. Okay. Okay, I can understand why you picked this as one of the research projects that you're most proud of. And might I say, I love the title, Everything SAXS.
Yeah. It is so cool. I think it's really worked with making the paper more popular, right? And that's so every year I also give a lecture about
Everything SAXS.
No, about the dark side of science. Research misconduct, things like that, and why research misconduct happens, and and part of this is the chase for these metrics, and metrics like H-index and so on. How do you boost your H-index? Well, you make sure you get cited. How do you get cited? Well, you choose really catchy titles for your papers. So
definitely.
This one was good. Another one that was really good was by somebody else. An absolute blast to read. It was. Will any crap we put into graphene improve its electrocatalytic behavior?
Oh, I remember this. I remember this. This was like 2 years ago, I think. I remember 3 years ago. I remember this.
Great.
And I was like, oh, yes, this is the title. Can we just make all the scientific papers, paper titles, like really catchy and really funny?
Yeah,
definitely.
Yeah, hey, I mean, these are papers that we write, right? And we don't get paid for this. In fact, we need to pay for it. So why can't we make it a little bit funny, right? So.
Exactly. Might as well have some fun with it. Definitely. So, Brian, it sounds to me that the research aspect of being a scientist is something that you really enjoy. It's close to your heart. But other than the research itself, what else do you like about being a scientist?
Yeah, it is. I must say it's far from perfect, right? There's a big guilt feeling that comes with being a scientist with a permanent contract. As I mentioned, I look around at my colleagues and I'm like, oh, they really also deserve. They also really deserve permanent contracts, and they really deserve to have some stability in their lives if they want it, right? Of course, you can always move, and you can always want to move. So that's sort of the downside of these scientific careers. I also feel really sorry for my British colleagues who are currently suffering from lots of trouble in the academic world when it comes to workload, as well as pensions being cut, for example. So yeah, there's a lot of trouble going on in science, but every now and then I manage to shut myself in my lab, and I have all the toys there, right? I'm not really lacking in anything, and when I do lack in something, I just go to the basement and I scrounge around, and maybe I find something else that I can use. Or go to the workshop and ask them to build me that one piece that I'm missing. And when I'm in the lab and I have a problem setting, I go to the shelves, pick one thing, pick another thing, and try and solve that problem in an innovative way that maybe we didn't think would work. And in that sense, it's really important to remember that you can always try, and you should expect to fail, right? There were some cases where I thought, okay, I will try and make a simple version of this instrument, otherwise that people would make really complex setups for. I was like, I will try to make a simple version and see how far I can get with 3D printed parts and cheap bits and pieces, and then you might find out that it actually works better than you expected, and that is really nice. So I can, maybe it doesn't have a lot of scientific value, but it certainly gives me the experience in building up pieces of equipment and putting stuff together into an integrated system that that later on might help in another project, right? So when we get scientists to come to us, we can, and they have a particular question or a particular problem setting, or they want to do an experiment where they do a reaction on this side and they need to start it at a particular point and then monitor it. Then I can go like, okay, in that case, we can put this together with that together. And I've already tried out half of these things, right? And it's the same whether it's hardware or whether it's software. So I also write a lot of software and code to analyze people's data. I do a lot of different activities. I dabble a little bit in robotics as well. And all of that playing that you do in the lab, essentially, can at some point come together into an integrated system that can really help one of our colleagues. So, so yeah, that's why I always recommend, especially students that work with me, to always play. Right. If you have a 3D printer or if you have a laser cutter, like what we found in the basement, then don't be afraid to play and use it for printing something, printing something that may not have anything to do with your work. Right. The more you work with these pieces of equipment, the more you try out, the more familiar you get with it. And then next time when you have a scientific problem, you might then go back in your head and go like, oh yeah, no, I can actually use that, and I know how to use it, and it won't take much time at all because you're familiar with it. So that all, even though it looks super chaotic, it can actually be super useful in the end, right?
Yeah, and it all comes together at the end. The chaos, you do find a story within the chaos. Sometimes, of course, of course. So, Brian, I mean, you already shared several advices here, but if you were to go back in time and talk to the younger Brian, what advice would you give him, or to the students who are starting their research journey today? What pieces of advice would you give them?
Yeah, I am. So what I currently tell students is that, okay, science is certainly a career. It's certainly not an easy career, and career opportunities are super limited these days. So make sure you also look at industry, right? Industry is not the devil that sort of lurks behind, and that is that there are many people on Twitter that have found themselves very happy changing a career from the scientific world to an industrial world. And I would definitely recommend students and people to keep their options open, keep those contacts with industry, try to establish new contacts with industry. I think you'll find that they're actually much more amenable than you might think, right? And you can ask people for samples. You can ask what they're interested in. Maybe they're interested in what you're doing. You can invite them over. It's super friendly, super helpful. I've certainly had a lot of good contacts with industry, and I wouldn't hesitate for a second, to switch from the scientific world here in academia to doing science or research for an industrial partner. Yeah, some of the wishes that I would have.
Well, if you have 3 wishes, what would you ask for? And I'm not promising anything here, okay? So tell us about your wishes.
Right. In terms of wishes, I really wish there was more stability in science, right? As I said, for a scientist to be in their 5th postdoc is incredibly off-putting, is incredibly downheartening. I mean, and even though I see the starts of the development of this in other industries, I think the standard still should be that we give people permanent contracts. And if all of the institutes and all of the research environments would give people permanent contracts standard, just like industry does, then you wouldn't have to worry about people staying if they don't like it, right? Because that's not the way it is in industry. If somebody doesn't like their work in industry, they're not going to stay forever. they're going to find another job where they will get another permanent contract. So as scientists, we've really shot ourselves in the foot there. And like, as my wife likes to remind me, she says, yeah, I don't know why you did that, because I thought you were supposed to be the smart people. But,
but that's a very good point.
but I don't think so. I think it's just research, and researchers are no smarter than anybody else. But it does make for a funny story.
Definitely. So that's your first wish, to have more stability and a longer term contracts for your colleagues. What's your second wish and the third wish?
I would really like to see an increased diversity in the workplace. Now, it is improving slowly, very, very slowly. And this is something an acquaintance of mine on Twitter explained to me. This is, you don't have to wait until you get so much diversity in the workplace that it's all evenly distributed, right? This is something you can force initially. So you can encourage the hiring of more diverse people if they have the same qualifications. And that is certainly a tool that we have in our hiring options at the moment. So if the qualifications are equal, we are indeed encouraged to do this, and I'm very much a proponent of that, because I find that having this diversity in a workplace, it encourages innovation. I mean, it brings new viewpoints. It brings alternative ideas to the table, and that is super interesting. I mean, I'm perhaps lucky in the laboratories that I've worked in and the laboratories that I've set up that we could really push this, and I think it's really paid off. So I definitely hope that we can increase this dramatically.
That sounds good. So increased diversity in the workplace. That's your second wish. What's your third and last wish?
Well, that one is a bit of a selfish one. I mean, I just want to. I just find that I'm the happiest when I'm in the lab actually actively working on something, and I don't have to worry about some of the administrative things that I might have to do, or meetings that I have to do for. These things that distract you from what you were actually hired to do, right? You were hired to do science, not to fill out forms and things. And we are relatively lucky in that we have a super helpful secretarial staff that we can offload a lot of this work to, so that we can focus more on science. But there's still a lot of our time wasted in meetings that could have been a lot shorter, or meetings that could have been a lot more organized, so we get to the point quicker, and we can make a decision and move on, right?
Right.
So my third wish would be that we'd really be able to free up our time to do the experiments and the developments that we are supposed to do.
That makes sense. All three wishes of yours: stable contracts, more long-term contracts, diversity in workplaces, and more focus on science, or more time to do the actual science than the bureaucracy. All three very, very, actually, I would say realistic wishes. I'm not sure about the first one.
Yes,
but
yeah, I really hope that things will change in the first one. There were some moves by the German government recently to improve this, but they might have formulated it in a way that doesn't
really
work.
help.
Yeah, that doesn't really help. So
right.
Yeah, tricky.
Yes, definitely. So this was really amazing, Brian, speaking with you. I really enjoyed our conversation about your science, your life as a scientist. But before I let you go, one last question I have for you. And of course, we cannot record podcasts in 2022 without addressing the giant elephant in every room, on every street corner, and that is the pandemic that we are living through. So what are your learnings from these challenging times that started about 2 years ago?
Yes, I did prepare for this question, but I want to change my answer.
Please go ahead, change your answer.
This is so initially I said, I mean, my answer is still valid. My answer was, don't wait forever to do what you want to do, and
Right.
make sure you take care of your mental health and find or force that balance between life, family, and work. And that is so true. But one of the things we started in 2020 during the pandemic was online lectures. This online lecture series that I talked about, I think we were one of the earlier ones that really started something, and that's because we didn't try to plan everything, right? And that reminds me of this quote which appeared in the TV series The Expanse. Now it was attributed to Xerxes, which says, "Plan and prepare for every possibility, and you will never act. It's nobler to have courage as we stumble into half the things we fear, than to analyze every possible obstacle and begin nothing. Great things are achieved by embracing great dangers." Now, I don't think we're doing anything dangerous, but we've certainly found that during the start of the pandemic, we could just do things and we could just try things. And even without a lot of planning, even without a lot of preparation, we can find out how this works, if it works, right? And that was more fun, and it was a very, very quick development that we could do. So go out and play, essentially, right?
Yes, I love that.
Don't prepare all of these documents. It's not necessary. You can just do.
Yeah, go out and play. Just do it. No copyrights from any shoe company or anything. On that positive note, thank you very much again, Brian.
You're very welcome.
Forward to having you on Real Scientist Nano. Thank you.
You're welcome. Oh, looking forward to curating the series.
Thank you for listening. This is Pranoti, host of Under the Microscope. To know more about us, visit our website, thesciencetalk.com, and follow us on Twitter at realsci_nano.